And welcome to the session on vision sensing and perception. My name is Dario Gavrila. I'm with the TU Delft, formerly with Daimler, and I'm the session chair. And with me is the session co-chair, Christoph Stiller from the Karlsruhe Institute of Technology. So we would like to ask, before we start, the speakers to line up about 5 minutes before their talk over here to get a headset. The time slots are 17 minutes. After 15 minutes, Christoph and I will increasingly intensively gesticulate to the speakers. And so let's get going. It's a very interesting session. The first talk in this session is titled Semantic Stixels, Depth is Not Enough. And it's work by colleagues at Daimler, at ETH Zurich and TU Darmstadt. And the presentation will be presented by Lukas Schneider.
Yeah, thank you very much for the introduction. My name is Lukas Schneider. I'm presenting today Semantic Stixels. I hope that I can convince you today that, especially for Stixels, that depth is not enough. So I'm coming from Daimler, and this is a joint work together with researchers from the Image Understanding Group at Daimler, the ETH Zurich, and the TU Darmstadt. Many of you know already the Stixel word that uses stereo vision to distinguish between the flat ground surface and obstacles in the scene. So what you see here is an output of this algorithm, and we see here on the left and on the right there are probably cars standing, so we see the obstacles in gray. And in the back there is a building, and in front of it probably some kind of fence. This representation was used already in practice, so for example in the Werner-Benz drive. And we learned in practice that it's very useful because it's very compact and it contains this information that you need about the free space and about obstacles in the scene. However, there remain a few problems. And one of these problems is this fence in the background are actually pedestrians. So it's not enough to know about what is an obstacle and what is not. We also want to know for each of these stixels, for each of these objects, what kind of object do we have here. So this is the first problem. This is the second problem. What you see here is a flat road surface and then these weird obstacles in front of us. And what happened here, if you look at the images, we are in San Francisco and we have this complex road surface. Now, the Stixel uses a road surface estimation, which is done previously, and this can fail. So for example, in San Francisco, this happened, and we had these obstacles, and of course we don't want this. Probably we could solve this based on depth in scenarios like this. However, this is very difficult to do robustly, for example, if you have reflecting road surfaces. So this is a very hard task based on depth only. Finally, there are difficult classes. So what you have here is a complex road scenario. We have cars, we have traffic lights, we have traffic signs, we have building, and we also have the sidewalk that you can see here on the left and on the right. Now, unfortunately, the sidewalk is not correctly distinguished from the road surface. And of course, this is very hard to do based on depth robustly because it's just a slight deviation from the ground surface. It's very hard to do. So yeah, depth is not enough. And so we present today semantic stixels. Now we see the output of this algorithm here, and we now have this colorful world where each of these stixels has an additional color that encodes the semantic class of the stixel. So now we have in pink here on the left and on the right the sidewalk. We have the persons correctly represented. We have the traffic lights here. So overall we have a very rich representation, which is compact still and very robust, and also efficient to compute. And we do this by leveraging recent successes in deep learning, and we show how this can scale with even a high number of semantic classes. In evaluation, we will show that we achieve superior results to the existing methods. Okay, so how was that done? Let's have a look at the overview. What we have here on the left are two inputs that we use to generate this joint representation, geometric and semantic representation, that can then be used in all the high-level tasks, for example, localization and mapping, or whatever else you would do with computer vision. As input, we have stereo matching, so therefore we use semi-global matching, that's already available in real time on dedicated hardware today. And we have a semantic labeling that gives you a label for each pixel in the image. And this is done by training a fully convolutional network, which is based on the Google Net, and with only a few slight modifications. And the main advantages of this architecture, it's very efficient to compute, and it gives you very good output. So what you get is for each pixel a probability distribution over all the classes that you trained it with. So for example, we have here two classes, person and road on the left side, on the right side, and a high probability is encoded with a red color. So for example, we see for persons that these are correctly recognized by the system with a decreasing likelihood if you go to the boundaries of the object. Okay, so we have the semantic labeling. Now the question is, how do we combine this information to get a good representation of both? And okay, let's do the easy part. Let's take the naive approach and just take the sticks as they are, and take the semantic input, overlay them, and take for each pixel the best possible label. And it looks quite well, right? Actually, if you take a closer look, what you see is that here on the sidewalk, we didn't correctly recognize it, although the semantic labeling correctly detected the sidewalk. Okay, so the same happens here in the sky. And also we have a 3-meter tall pedestrian standing in front of us, which is rather unlikely. So what happened is we take the sticks as they are, so we cannot recover from errors. We have a semantic class for each stick, which solves the first problem somehow. But if we look at the second and the third problem, we couldn't solve it because we cannot recover errors in the stick segmentation. So second problem, the complex road surface in San Francisco and these difficult classes, the sidewalk on the left and on the right, cannot be solved with this method. So instead, we have to take both inputs already in the generation of the Stixel representation. So let's take a closer look to that. So Stixel is actually an image segmentation into these vertical Stixels, where each Stixel can have one of three classes. It could be ground, which is flat. It could be object, which is upright standing, and sky, which is very far away. Now the algorithm works as follows. You extract one column of the depth input and formulate an energy function for this column. And this has a data term and a depth term that is formulated for each Stixel. And that rates how well the current Stixel fits to the depth input. So we minimize the depth error of the representation. A second term, a pairwise term between neighboring Stixels, captures something like, okay, we have a road Stixel here, and it's very unlikely that we will have an object below the road surface, so this captures these kind of priors. Now you can optimize this function, globally optimal, using dynamic programming, and what you get is one solution for a column. You can do this in parallel for all the columns in the image, and then you get the Stixel world. Now the question is, how do we bring in now the semantic additional input? And okay, so what we do is we add an additional data term that rates how well fits a Stixel to the semantic input. So now a Stixel doesn't have 3 possible labels, but in this case 19 semantic labels. And we look for the most likely label and maximize the likelihood of this label. So in this case, the Stixel, you can see everything is green in the semantic input, so this would be probably a tree Stixel. Now, unfortunately, the dynamic programming has a quadratic computational complexity with respect to the number of classes. We show in the paper how this can be reduced to a linear one with only a few approximations. So we can also scale to a high number of semantic classes, and we think this is important in the future because the complexity is very high and we need a lot of classes to understand the scene. Okay, now I show you the results. What you see here is a drive through Stuttgart, and the labels are end-colored again by the colors. So what we have here are cars on the left, on the right, we have the road in front of us, but also we have these complex classes like traffic light on the left and on the right. In gray we have poles, and we have the sidewalk in pink. So this representation has all this rich information now included, and it's very accurate. At the same time, you will not observe any phantoms standing on the road, which of course is very important because we don't want to brake because we saw some phantom object in the scene. Yeah, we all know that we can select one nice sequence where our algorithm performs well, so let's have a look at the numbers. We evaluate ourselves on the cityscapes dataset, which is highly complex scenarios with a high number of classes and a high number of images. However, we don't have depth ground truth, so we also wanted to have a look at how well our algorithm performs in terms of depth accuracy. So we also wanted to look at the Kitty dataset, and luckily Ladicki et al. Annotated densely stereo and semantic ground truth for 8 classes. And we use this for training, and then we can evaluate on this dataset and on the well-known Kitty 2015 dataset. We compare ourselves, our method, with this naive version I told you before. And also there's a similar approach that uses for the semantic input random decision forests. So we compare ourselves to this approach, and you see an example output of this on the right. Okay, let's have a look at the depth performance of the approach. We measure this in terms of depth error, so high percentage is bad. Our input, the semi-goal matching, achieves 20% disparity error. And now, recall that stick cells are made for compactness and for robustness, not for highest accuracy. So we were actually quite surprised that the algorithm performs superior to the SGM pixel-wise input. So we achieve here a 16.4% approximately, 6.3. Compared to the Stixel baselines that we have, we see that both are outperformed significantly. The same holds on this Kitty 2015 training data set, that however this gap to the input is relatively small. And this is due to the fact that we have ground truth in Kitty 2015 only in the lower part of the image. And we think that our algorithm mainly helps in the upper part where you have trees, we have sky, where stereo vision typically has problems. Okay, so let's look at the semantic performance. We measure this in terms of intersection over union, so high percentage is better. And our input achieves 70%. Now, again, the Stixel word is made for robustness and compactness, and it still achieves 66.4% intersection over union, and we're quite happy about that. If we compare this to the Stixel baselines, we see that both are outperformed with a great margin. This indicates now that this joint inference that we make is superior to all kinds of post-processing methods that you could do on the existing Stixel world. The same message holds for the cityscapes dataset, but this gap to the FCN input is very small, and this is due to the high resolution of cityscapes. So this quantization in the Stixel columns has a weaker impact, and so we almost achieve the same accuracy. Now I talked about compactness all the time, so let's have a look at that. Our input, we have a 2 megapixel camera in cityscapes, so we have 2 million of measurements for each pixel measurement. And if we look at the Stixel world, we only need 1,400 Stixels to achieve the same or even better accuracy compared to the input. And we only need like 300 or 400 more than the both Stixel baselines. Okay, so let's compare visually to the geometric variant. We had this example at the beginning with the pedestrians in the background. And we now see, okay, we have this semantic class, we have this semantic information now included in the representation. So, first problem solved. We had this example in San Francisco. Now, semantic guides the optimization to treat this correctly as road. So, we also solved the second problem. And finally, the difficult classes, like sidewalk, are also correctly represented. So now we have this rich semantic and geometric scene representation, which is compact, which is robust, and still efficient to compute. And it has superior performance to all the existing variants. Thank you very much for your attention.
Thanks very much, Lucas. We have time for 1 or 2 questions. Over there.
Yes, thank you. My question is how long does it take to process one image and put all the labels and so on? I mean, how close are you to sort of real-time?
Correctly, yeah. The question was if this is...
how long does it take? I mean, is it sort of real-time or...?
Yeah, so we have a 15 Hertz. So by pipelining, you can first compute the fully convolution network and then compute stick-sets. And at the same time you compute the stick-sets, you can already compute the fully convolution network on the next image. So we can pipeline this. And in doing so, we achieve real-time. So it's 15 Hertz, if you want so.
We have time for one more question.
Maybe I can just extend the question. So you achieve real-time using a bunch of computers in the compartment, or
sorry, no. It's a graphics card. We compute the Titan X, or we compute the fully convolution networks, and the rest is on standard CPUs.
Okay,
thank you.
Okay. One more question from the audience. Mohan here, please.
You have to wait or?
No, just it's coming.
Thank you. Very nice presentation and very nice last slide where you tick marked all the hard problems. Tell me one that is still not solved.
That's a good question. Yeah, we will see so we have to look at robustness to difficult scenarios. We have to look at bad weather, for example, so really bad weather. We will see how well the fully convolution network will perform in these cases. We don't have the training data, so ImageNet, I think most of it is not bad weather, so we need training data for that. So these, I think, are the scenarios we have to look at.
Thank you.
Okay. With that, we thank you also once again. And while we change the laptops and presentation, I may already announce our next talk. Next talk is presented by a team from Carnegie Mellon University, Pittsburgh, USA, and it's entitled Map Supervised Road Detection, so well suited to the last presentation that we've just seen.
Can you hear me properly? Yes. Okay. Good morning, everyone. My name is Luis Navarro, and I, like the presenter mentioned, I come from Carnegie Mellon University. I am part of Professor Marcel Debert's group. We work on our advanced perception systems for autonomous vehicles. This is work done in conjunction with other people, as you see their names there. They deserve pretty much all the credit for this work. And today I'm going to talk about our approach to map supervised road detection. So the scope of this work is as follows. What we wanted to set up to do is to detect the drivable road in front of the vehicle using images from a monocular camera. That is what we wanted to do. But in doing so, we realized that there is a lot of work that we could do to simplify and to make more efficient the production of training examples for new classifiers, for new detectors. Because, as I'm going to explain in a bit, it takes a lot of time and effort to do so. So currently, this is done in the following way. You probably know about this, but you collect a bunch of images, and then you're going to have people that are going to go one by one labeling these images to produce training examples that then we're going to use for a classifier. When I say label, you know how it is, right? You're going to start drawing a polygon in all the areas of the image that represent the class that you want to detect. In this case is road. And as you can imagine, this is painfully slow. It's labor intensive. And it's not easy to do. People get tired. Even if you pay people to do it, after a while, you're not going to get the results that you want. Not everybody is equally good at labeling. Some are very persnickety. They label every single thing. Some other people are very sloppy. They just, you know, just a curve and they are done. So we would like to address that. Anyway, after people are done labeling training examples, you go ahead and train a classifier. And then when this classifier is trained, then you can just go ahead and input images, and you have a labeled image at the output, right? In this case, we would like to detect the drivable road. So this work aims at do something about that bottleneck in there. So we started the question, what can we do to alleviate the situation? Perhaps we can do something. We reviewed the previous work and we decided that to eliminate or minimize human intervention, we can add additional data information during the data collection when we collect the images properly. And we decided to go with these two elements. We're going to stamp a vehicle pose information from these sensors that you see on the left to each of the images that we collect. And then in addition to that, we're going to use the information contained in a roadmap. So we propose the following framework to do that. We're going to start collecting images, but with the additional data that I just mentioned. Then we're going to run our approach on those images, in which, in combination with the new augmented data, we're going to use the context provided by a map. In this case, we use the OpenStreetMap. I am pretty sure you are familiar with that. It's open source, it's free, and it's quite complete, and you can add to it. We also take into consideration the camera calibration, both intrinsic and extrinsic. We run our approach to produce the set of training examples. We train our classifier, and then using only the image data, we can run our detector. So that's what we wanted to accomplish. How do we do that? Before I do that, mention, I'm just going to say that there are other people that have tried to use map information in these approaches. But as you can see there, some of them use the map information, but then for training. But there's also a certain degree of human intervention still required. We wanted to move away from that. Similarly, during the test time, when it's running online, some of these approaches still need to have access to the map. We didn't want to do that just to simplify things. We just wanted to operate with the monocular camera. So the approach that we propose uses maps to label the images collected at ground level as the vehicle sees them, and without any human intervention. And when the classifier is running, it does not require either the map or the sensor information to do its job. So this is our approach. It's basically two steps. The first step is the initial labeling, and we're going to try to project the map information, the information that is contained in the map. We're going to try to project that onto the image plane. Since this is not a perfect world, this is not going to work right away, we need to do some refinement. So this subsequent step is going to try to improve the initial labeling based on the appearance features that we see on the images. Let me elaborate on that. First, the map projection. What we're going to try to do is basically to look at where the vehicle is with respect to the map. We're going to register the location of the vehicle inside the map. We're going to look at what the vehicle may be looking at according to the information contained in the map. And then we're going to try to reconstruct that scene and try to project that scene, try to overlay that scene as how it would appear in the image that we collected from that position. So the overlay should look something like that, right? For example, if I know where there is a silhouette of a building, where is the road, I can do something to try to have an idea of what the vehicle may possibly be looking at from that perspective. As you can notice, I use the word approximate 3D reconstruction. The maps don't contain everything you need to do the reconstruction. For example, the height of the buildings is usually not contained. Similarly, there are other constructions. For example, in the picture to the bottom left, you see a small wall. That is not contained in the map. So there are elements in there that are not contained in the map. So this is not perfect. We're going to need to do some refinement. Other errors that we see in the map projection As you can imagine, well, vehicles, other integrants of the dynamic scene are not contained in maps. So we may see vehicles, but these are not represented in the map information. We're going to miss those. Similarly, the map information is not perfect. This is an example in which the road reported in the map is actually wider than the actual road on the street. So that's an error. And finally, you can imagine that the localization system is not perfect. We're going to have errors in the vehicle pose estimate. So things may look a little bit off. So this is step number 1, and that's why we need step number 2, which is the refinement step. In this step, we start with the map projection. And well, basically the intuition of what we're trying to do is to look at what non-road pixels look similar to road pixels according to the map projection. We're going to try to cover the areas that we didn't cover first. And similarly, we're going to try to look at what things that look like road, that doesn't look like road, are still labeled as road, right? So that's why this is appearance-based. To do that, we're going to do clustering based on color features. We are going to transform the image to 2 different color spaces, but then we're going to just create a space using H, S, CV, and CR, and we're going to do a clustering of the pixels in that augmented space. Then for each cluster, we're going to try to determine whether the cluster represents a road or not road, and to do that, we find the road to non-road pixel ratio. Now, there's typically an imbalance in the number of pixels that represent road versus the one that doesn't represent a road. That requires an additional normalization step that we need to do for this to function. And the end result is we're going to label each cluster as whether it represents road or not. We use the L method technique to determine the number of clusters. So even that step we do automatically in this step. And then after we label all the clusters as road or not road, we project that back to the image, and that's what you see there. Now, there are some things that were done correctly. As you can see, for example, some of the pixels that were not initially labeled as road on the bottom, let's say to the center, to the right, now they are labeled as road, so that's a good thing. Similarly, the road pixels mentioned on top of the vehicle are gone, but you also see some incorrect labeling. For example, that band that you see on top of the figure, that is labeled obviously incorrectly. And you probably don't see it, but there's a bunch of other red dots splattered all over the image. To eliminate those, we do an additional step to constrain to the road candidates. And to do that, we just do a super pixel segmentation. Then we apply a threshold on the GEPB field. And what happens is, when you do the super pixel, we're going to look at how far away from the original projection of the map that super pixel was labeled. If it contained a minimum number of road pixels, then we say, okay, this belongs to a road. And the end effect of that is that we're going to see whether the super pixel candidates are actually good candidates as road or not road. And you see that we trim quite a bit of the noise that we were seeing there. We do one last step, which is to eliminate multiple roads. We want to detect the drivable road ahead of the vehicle. So the opposite lane, we are not that interested in detecting that, so we eliminate it by just extending into the largest connected component, and that's what we keep as the road. And then we're done. We do that for all the images, and we create a new image training data set. So these images are all labeled automatically. So the purpose will be at the end to train a classifier. In this work, we decided to go with a fully convolutional network. Initially, we tried this one that turned out to be a little too slow to train, and the output was pretty coarse. The stride of 32, the image was pretty small. We wanted to have something with a higher resolution. And I don't know if you noticed, my colleague that spoke before me, he also used the same, so I guess we read the same paper. But we're using the exact trick that they did. We didn't do any groundbreaking work in terms of the detection part here. But this is exactly what we did. The advantage is that we reduced the complexity of the computational complexity for training. We increased the size of the output image, and we increased the memory efficiency. All of that is mentioned in the paper. So that's basically what we have. To evaluate how this thing works, there are two aspects to it. One is the label generation, how good the automatically generated labels actually are. Did we do a good job producing the training images? And the second is related to our target application. If I were to use those trained images, how good the classifier is going to work in the end, because that's what I set out to do initially. How well does the classifier do with that? To evaluate this, we use the Kitty dataset. I don't know, I imagine a lot of people in this room are familiar with that, but pretty much this is data that is collected by this team of researchers in Germany. It's very good. We have all kinds of data. We have images. We have labeled images. We have the ground truth for testing. We also have vehicle pose, etc., etc. So that was very convenient. For the evaluation, we also use the Kitty provides a homography, so you can do a transformation for a bird's eye view. So we can do a more fair comparison. So we're looking at things from above, as is indicating there for our evaluation. And first, in terms of results, let's have a look at how good the labels are. So this is what we have. On the first row, it would be the approach, including the two steps, map projection and refinement. And the second row would be just the map projection. So you can tell that the refinement significantly improves the results that you get exclusively with the map projection. And just to compare with some other approaches, we compare with Alvarez's approach. They also do an automatic generation of labels, but they use fully connected conditional random field operating on multiple images simultaneously. So that's different from what we do. And you can see that we compare quite nicely with what these researchers are doing, although our approach is a little simpler to program. It's actually quite simple, what we did. So the images, how do they look? Just to have an example of successful cases. On the top, we see only the map projection. On the bottom, we see the results after the refinement. And you can tell that it does a fairly good job, in these cases, trying to refine the original labels. Not everything works, of course. And we see that in some cases, we have detected instances in which we do worse after the refinement than we did originally with the map projection. And we have noticed that we confess that we still have trouble dealing with shadows. We need to do a better job. So for previous work, this is something that we're currently looking into that. We need to do better in that sense. We also need to incorporate something to detect these conditions and adapt to them. Okay, this is in terms of the generation of labels. Now, row detection. We train the fully convolutional network that I mentioned before. We initially used a model trained by somebody else. We didn't train the network from scratch, but we produced a set, I believe it was in the 600 examples, and we refined that model with the example that we have. And this is the results. And the top is fully supervised, which means this is compared against a classifier trained exclusively with images labeled by humans. And then we see our approach, how it compares. It does actually quite a good job. Just to make things interesting here, this is approach, again, by Alvarez. They also use a convolutional network. But they do things differently. They don't use the map information. They do an analysis on the structure, the geometric structure of the scene. They try to detect, for example, what is vertical, what is horizontal, where is the sky, things that we may know about the scene, and they use that to produce a prediction of where the road is. And we seem to be doing better than them. And finally, these two approaches are different. They use different sensors. This one uses stereo camera, and this uses Velodyne data, and you see how it compares. And these are some of the results that we get actually with actual images, and it's it tends to do a good job. Well, in summary, that's what we produce, and it's a simple algorithm to program. It's not complex at all, and details are in the paper. And we actually managed to reduce the, I don't want to say completely eliminate humans, but yeah, we don't depend on human labors as much as we originally did. So for us, that was a big gain. So I'm going to leave you with that, and thank you. And if you have any questions.
Thank you very much. We have just time for one quick question. Yes.
How does the weather affect the labeling generation?
Can you repeat your question again?
How does the weather affect the weather?
The weather. We have not found a good set of examples with bad weather. In the Kitty dataset, I don't think we have some like that. We have collected some other images from our own vehicle. We have a Jeep Wrangler, and unfortunately, because of the other sensors the vehicle has, we don't take it outside in bad weather. So that has been an issue for us to get a hold of those images. My intuition is that it will work, but that's exactly the point that I am trying to make. If I wanted to refine or adapt a classifier to a new road condition, I need to incorporate new examples that reflect that condition. If I go outside and then I try to collect data under bad weather, then I need to have people labeling the new data, and that is a problem. The approach, the current framework, doesn't escalate that way, doesn't scale that way. So that's my answer.
Okay, I think we'll have to keep it to that, and we thank the speaker again.
Thank you.
So the next presentation will be by Quan Phu Thanh from IBM Watson Research Center, and he will provide us a closer look at faster RCNN for vehicle detection.
Yeah, better? Okay. My name is Quan Phu Thanh. So today I'm gonna take a close look at fast RCNN for vehicle detection. And this is a joint work with my colleague Lisa Brown, John Smith. As we all know, what's happening? I don't know what's happening. Let's switch to.
Control L.
Yeah, just okay, thanks. Sorry about that. I don't know what's happening. Suddenly all the slides are gone. Okay. So basically, okay. So as you know, there have been a breakthrough, in object detection with deep learning. One of the winners apparently region-based convolutional neural networks. As the model goes deeper and deeper, you can see RCNNs is increasingly achieve better and better performance on the VOC benchmark for genetic object detection. For vehicle detection, we observe a similar trend. So last year, I think the best published results were 3DOT. These are the top performers from the Kitty website. So as you can see, in less than a year, the results have been updated, I think, more than 10 times. However, the FastRSN doesn't look like a forerunner in this computation. So basically, if you use the original setting and train a FastRSN model on the Kitty data set, you will actually only get probably about 60% average precision on this data set. So if we tune this model, I guess we can kind of boost the performance to about 80%, which still worse than the state of art. So today I'm going to talk about how we actually can tune the model and to significantly improve the performance from 60% to actually to around 80%. And I will also talk about it how we can further improve the performance without significantly actually changing the framework of the RCNN. First, let me give a very brief description of this model, FastRSN. So basically, it has two parts. The first part is a region proposal network, so which basically it's like a sliding window-based approach. It scans about 9 anchors at each pixel at the very last end of a convolutional layer. So this anchor basically is a bounding box with a specific aspect ratio and a scale. It classifies each anchor into an object or non-object, and also find basically it also do a regression to improve the localization of the bounding box a little bit. So after that, it sends a set of bounding boxes with high objectness and the coarse localization to the fully converted layer here. And this part does two things. One is it classifies each candidate or proposal into different type of objects, and also it has another level of regression to further refine the localization. So as you can see, this approach can consider as a two-step approach. The RPN provides the coarse localization, and the RCNN further refine the localization. And the network could be of any type of convolution CNNs like NXLET or GoogleNet or VGG16. So actually, we use the Kitty dataset for our experiments. Kitty dataset has 3 different categorization categories on vehicles: easy, moderate, and hard, depending on the size, occlusion, and cropping of the vehicles. We actually use 2/3 of the development data set for training, it's about 5,000 images, and the remaining for testing, it's about 2,500 images. We use VGG16 and adopted the same setting used in FastRSN. So unless we specified in the experiments. We also use the same metric for performance evaluation, average precision, and those are computed by the evaluation tool provided on the Kitty website. So the related things in FastRSN we look at are the image scales, both the training scale and the testing scales. So we also look at the object proposals, how many of them, how many object proposals are appropriate for getting better performance. And another thing is the angles, number of angles, especially the scales of the the angles. These are very relevant to the performance, as you will see later. As I mentioned, FastRSN basically is a two-step approach or two-stage approach.
So actually we can iterate, the approach with more steps. We'll look at, that as well. Okay. Now the first thing, let's look at the scale. Actually scale is a very important thing in object recognition. FastRSN, actually has kind of, built-in capability in handling scales because it's used object proposals. We basically train different models, train multiple models at different scales. For example, at 1,000, 1,200, 1,500, and 1,800. So basically, this scale is a training scale. It refers to the longer side of the image. If you look at this chart, basically you can see, basically the larger training scale tend to produce better performance. However, if we combine all of them, the performance doesn't improve at all. So basically means multiple scales training here is not very helpful on this data set for vehicle detection. So interestingly, if we look at this chart, so basically we train the model at some scale, then we test it at a relatively larger scale. For example, here, if we train the model at 12,000 pixels, and we test it on 1,500, 2,000, even larger. So we see actually the performance tend to improve quite a bit, especially for this moderate and hard examples. This basically means this FastRSN, I would say you could say it's scale invariant, kind of scale invariant, but actually it's probably not exactly scale invariant. We kind of speculate this is caused by the distribution of the objects on the KITTI data set. We also look at the number of objects, how they affect performance. So basically, as you can see here, as we increase the number of proposals in FastRSN, the detection tends to not change. Detection performance tends to not change too much. We only need a very few very few proposals here to get the performance from the algorithm. If you increase the number of proposals, you do see actually we have more difficult examples included in the testing. However, they cannot convert it to correct detection, which I will discuss in the next slide. Basically, the reason is so we know detection basically can actually involves two things. One is recognition, the other one is localization. So we define the localization capability of the model by the number of correct proposals divided by the total number of proposals. So when I say correct proposal, is that it has a higher overlap with the ground truth. So usually we consider 0.7. So basically, if we have a 0.7 overlapping with the ground truth, that will be considered as a true detection. So that's the localization. So we also define this correct detection basically. So you have a 0.7 IOU with the ground truth and also 0.5 classification score. So basically that's a correct detection. Use this tool, we define a conversion rate. Basically, how likely a proposal can be converted into a correct detection. So if you look at this, three plots here, so we can see on this moderate and hard examples. So even the localization capability can be increased when we put more number of our proposals there. But unfortunately, they cannot. If you look at this conversion rate, curve here, unfortunately, they cannot convert into correct detection. Basically means the classification fails here. This will suggest in any future work, we should consider that part, either improve the feature, the salience of the feature, or improve the localization of the object proposal, so then we can get a better features for classification. Okay, so another thing we also look at is number of anchors in region proposal network. So basically, in FastRCN, it uses a default of 9 anchors, basically 3 aspect ratios and 3 scales. Because the genetic object detection benchmark, we'll see it includes a lot of very large objects, so we can use a relatively large scales here. But for the KITTI data set, we also have a lot of small objects, small vehicles. So we actually add more scales. One is 4, the other one is 5. This gives like 12 anchors and 15 anchors. And we compare the performance here. So you will see actually it does help, especially on the small, actually moderate and hard examples. We can get like 5% or 7% improvement respectively compared to the default setting. So lastly, we look at this if iteration would help. So basically we take the network, basically the 2-stage network, and we retrain the RPN and then do RCNN again. You can continue iterate this, but we just do one more iteration. Basically we train RPN one more time, and we also train RCNN one more time using the same framework. So you will see, so this actually improves the performance, about 3%, on the moderate and the hard examples. So basically means, the iteration can, the iteration can improve the localization capability of RPN. You will have a better input to the RCNN for classification. Okay, so when we put everything together, we change the number of anchors. We actually use a larger training scale and test scale, and we also take the iterative approach. We run this final model on the test data set. So here's what we can get, is probably 88% and 80%, compared to the state of art. So here, I think, this is the results, by the time when we, wrote the paper. It's still, not as comparable as the best results, but I think we can do a few more tricks to further improvement the performance. So which we haven't done yet. So the first thing is, we know the object proposals are very critical for getting better performance. One thing we haven't explored is the aspect ratio. This definitely, if we, change this, I believe we can actually get, more improvement. Another one is this ROI pooling. So basically this, the default is 7x7. I think, for some type of, vehicles, or even especially the small size, and this might be very relevant. So we can actually tune this parameter to see if any performance can be any better performance can be achieved. So the other tricks, I think we can apply is context modeling. For example, we can just extract basically use a larger bounding box to include more context information in the features. And also hard sample mining, I think this is a very useful technique, and it's a proof effective in some other top of performance on the KITTI data set. If we try things like that, I expect we can boost the performance further, probably close to 90%, or on this easy examples, and maybe 85%, on this moderate examples. So I think with this I conclude my talk. Thank you very much for your attention.
Thanks very much for the interesting presentation. We would like to ask the next speakers to line up here for the headsets. And in the meantime, we have time for some questions. Any questions on Foster RCNN? Oh, there, Brandon. Yeah.
Hi, thanks for the presentation. You mentioned it sort of briefly at the end here, but can you say a little bit more about this idea behind Pascal VOC when you take ImageNet or these types of data sets where you have very large objects versus, here with autonomous driving or perception on the road where you have much smaller objects? I mean, clearly the RPN network is not designed for that. So can you say a little bit more about again, how you expect to tackle very small objects which you want to detect?
Okay. So I think, this is so object size basically are very related, for VOC. So we see basically usually the objects are pretty large, so the scales are not, so critical. Actually under this default setting. But for the vehicles, we have a lot of small objects. But as you can see here, because we use basically large training images, we scale up the images for training. Usually 1.5. In some other work, it's observed that even 2 times larger or 3 times larger can even produce better performance. I think this is partially handled by using larger training images. So
I think we have to kind of click on up.
Yeah, okay. So that's why you see the scale, when you increase the scale, you don't see significant improvement on the performance. But on face detection, I tried some other, on other data, because face are also small, the scales are very, very relevant, under this framework.
Okay.
Yeah, I hope this
okay.
The question.
Thank you very much. Thanks to the speaker again.
Okay. You notice we are a little behind our schedule, but we come to the last presentation of this session, which is given by a group of Cadence Design System. And it will be on hierarchical convolutional neural networks for traffic sign recognition.
Hello. Hi, I'm Piyush Kaul. I'm from Cadence Design Systems. So I'll be presenting on this hierarchical CNN for traffic sign recognition. Yeah, basically I'll go through first a little bit about, skim through the ADAS and CNN background and get into a little bit of the data set we used and what's the method and conclude with the results. So basically what we have is in the CNN is primarily used for the ADAS networks. The ADAS problem is actually, as we already seen, it's more like collision detection, object recognition. So CNN is part of many of these algorithms, or sometimes the main algorithm for object detection. The chain actually is, we have some initial signal processing and the signal processing pipe, and then we go through the extraction. So there's a detection phase where we identify whether the object is there or not, and then there's a classification part where we kind of classify the object. So the object is detected, it is there in the picture, and then we are trying to classify whether it belongs to which of those predefined classes. And the CNN is shown below, the structure of the CNN. So we have some input image in the pixel domain, and then we go through the successive layers of convolution, downsampling, and nonlinear networks. And there are many such layers, at the end of which we'll get some probabilities for different classes. Okay, and this is kind of putting the CNN in context. So currently the CNN is the, you can consider it the primary method or the most efficient method for, best performing method for object detection. And we'll see this in the context of ADAS, specifically in the context of traffic signs. So traffic signs, as we know, are for guiding the drivers. There can be a bend, there can be a stop, there may be some limits to the driving speeds. So there are lots of traffic signs, and these vary across countries, across geographies. And what we used for the sign recognition database was this GTSRB, the German traffic sign recognition database. This is compiled, this is around 50,000 images and some 43 different types of signs. Even though the number of signs may be much more, but this particular database has these 43 types of different signs captured at different lightings, different speeds by cars driving through. And now you can see the actual images. So these are the idealized, the signs as they should be, but when we see them actually, they are kind of much distorted. There may be distortion, affine distortions, there may be lighting effects, weather effects, blurring due to very high speed driving across. So all those will distort the actual captured image, and it becomes very tough to kind of identify. I'll go to, so there are some 50,000 of these, and these are unevenly spread across all these classes. And we use some 12,000 for testing, and rest for the training and validation of whichever algorithm we have. So there was a competition done, and basically these are the scores we had in that competition. The GTSRB itself was an online competition followed by a conference competition, and these were the different scores. So as you see, like all the top ranks were taken by the CNN-based algorithms. The only other algorithm mentioned in this table is the random forest and the LDA, but they are like the best is 96%, whereas the CNNs go about 99% also. And the human rank for reference is the 99.22. Because this is a security, the safety rated application, so the expectation for correct detection is very high. You usually shouldn't be failing too many times in, especially in ADAS related applications. So you're expected to get better than 99, better than 99.9, and how much better you can go, that's up to us. But the correct detection has to be very good. Okay, now in these signs, the other problem actually is that even though we have algorithms, not all of those algorithms can be implemented in real time. So if the algorithm is very complex, then it's actually only theoretically useful. It's not implementable in a real car or something. So the top performing one, 99.46, was the IDCA algorithm. This is also a CNN, but this is a committee, which means it's an ensemble algorithm, which means we run 20 versions of 25 networks of this CNN, 25 different CNNs all in parallel, and then combine, average the results. So this does give better performance, but the complexity is 25 times of one CNN, and CNN already is a fairly complex algorithm. Currently, so it's not that practicable. So our idea was how to have a very good performing algorithm, but with reasonable complexity. Okay. So these are some predefined groups, and you see these are kind of intuitively well defined, both in terms of like why they the functional classification and how they are designed also. So some of them are the speed signs, like you see, are in the circle, red circle with some number inside it, and then there are other probability signs again in circle with some cars or something inside them, and then like you see mandatory sign are the blue ones with some directional arrows. So for a human being it's very easy to distinguish between the between the classes. So these if for a human being, if you see the mandatory sign, you won't confuse it for a speed limit sign. But when we feed it to any algorithm, it may or may not be able to distinguish between these different classes. And as we see, there's a confusion matrix at the bottom of the slide. So on the left we have the best human confusion matrix. The confusion matrix is actually on the rows. There are the actual classes, the 43 of those rows for 43 classes, and the columns are what is detected. Now in this rectangular, the lines we see in the slide, this is kind of some kind of how actual sign was confused with what was detected. So these rectangular lines reflect the groups. So in the human thing, all the mistakes, which are the red dots, are within these rectangles, diagonal on the diagonal, which means that humans usually never mistake between the classes. And then on the right was the best performing CNN in the competition, and that is actually making a lot of mistakes because it is confused. It is making mistakes, but it's also making mistakes between the classes. It is confusing, for example, a speed limit sign with a danger sign or things like that. So one insight was how to reduce this and make it similar to human performance. So our idea actually is not to use the predefined classes. So a hierarchical CNN, the idea is we don't have one CNN, we have two layers of CNN. One will detect only the family, and the next CNN, based on the family, there will be another CNN which will subdivide, subclassify it, and find out which is the actual sign. So one CNN finds the family to which the sign belongs, the other CNN finds the specific sign. Now, as we saw, the CNNs themselves, so the machine may not be performing similar to a human being. So we are trying to find out what's the best way of finding these families also. What may be a good family for human beings may not be a good family for the CNNs. That's the idea. So we devised algorithm, we are calling it the CNN family clustering algorithm. In the sense here, the family itself is derived by the CNNs. So what should constitute a family is given by a version of CNN only. So this is actually the algorithm. So we find out from all the signs. So this is again the 43 cross 43 matrix, and in the image, and the colorful image, we are having this bomb signs, which means the correlation is high, and the dark ones, blue ones, means the correlation is low. So we are finding which are the signs which have good correlation, and we initially use the correlation to find out the seeds, the set of classes which are substantially separated out, and use only those signs to train a CNN. And once we have this kind of an initial version of CNN, what we do is we pass all the training images, all the class 43 class training images through this CNN, and find out to which particular which of these two classes it belongs to. So this is a binary classifier. We train a binary classifier based on the most distant classes only, and then used it to classify all the images into class A or class B, and then we recurse on that, which means that once we have these families, we have two families initially. We see whether the variance between those families is substantially small or not, and if and there are some other criteria also. So based on those criteria, we decide whether we want to further spread the families or not, and we get a binary tree. So this binary tree, all the leaf nodes are different classes. So these are the actual families we found out, which are not always intuitively clear why it should be, but the CNN seems to prefer these families compared to the predefined families. For example, if you see family 5, the blue sign, which is with the sideways oblique arrow, goes into family 5 with all because somehow the oblique line seems to be more important than the color for this classification. This is the hierarchical CNN actually. So what's going on is that we have a family classifier FC CNN, and then we have a member classifier MC CNN. So initially we train both the family classifier and so for the family classifier we train with all the possible input images. For the member classifiers we train only with the images for that particular family. So we'll get these ones FC CNN and 5 of those member CNNs, and then what we'll do is when we are testing, we'll pass the test image through the family CNN. It will detect the family, and based on the family, we'll pass it to the correct member classifier, and we'll get some detected class or some detected sign rather. So we are actually 6 CNNs, but for each test we are using only 2 of them, and the complexity is actually only slightly higher than a single CNN. The reason is that a family classifier is fairly simple and low complexity because it has very low number of feature maps. And compared to like the ensemble, which is 25 CNNs, this is like you can say 1.5 the baseline. And these are the final results we got. So we were able to achieve 99.82 with the CNN, and we used the color aspect also. And the bottom is actually shows the CNN, the features and all, feature maps and the sizes. So 32 cross 32 input was the pixels, but with color. And at the end of the CNN, we get the 43 classifier softmax outputs. But this is one member classifier, and all classifier will look like this one. And this is actually the confusion matrix after with our algorithm. So on the left is the predefined confusion matrix with the predefined classes. So if you use the predefined classes, we get the confusion matrix on the left, which makes mistakes outside the classes also, outside the families also. And on the right we have very much minimized any errors outside the family, and also reduced the errors within the families also. And that's all. Thank you.
Thank you very much for the presentation. Just one very fast question with for a very fast answer as well. Yes, Muad.
I enjoyed your presentation, but I'm confused.
Okay.
About 2-3 years ago, Professor Van Gool's group wrote a paper, very provocative title, that basically traffic sign detection is a solved problem, and the numbers that you are showing, 99, this does prove that. And there are other more complicated data sets and competitions that have come in the field in the last 3 years, and you have never mentioned that. Why?
So there are two aspects to the problem we are trying to solve. One is, of course, the detection rate, and the other is the complexity also. So we are kind of trying to address both of them. Low complexity, and so like I have mentioned a few more actually. I didn't go through the results. So there are better detection, some improvements in detection rate. For example, there's this 99.65 by Tsinghua also there. So people have used ensemble and very complex methods to improve the performance further. But our idea was try to keep the complexity about the same or reduce it.
Okay, so we'll have to leave it to that. Thanks to the speaker again. And this concludes the session on vision sensing and perception.